who have randomness. Pure math has it too. They're not any better than we are. You see? So to give an example of this, it just so happens that this week, I found out by chance, that this week there's an English magazine called New Scientist that comes out every week. It's like the English version of Scientific American. It's a little racier. It's a little more fun. And it comes out every week. And the one that came out last week, I don't know, the 26th, was that Friday or Saturday? It's the current issue. The next issue hasn't come out yet. Of New Scientist has as its lead article on the cover an article called Random Reality. And if you open this article, it turns out to be an article about the work of two physicists, very speculative work that says that what they're trying to do is they're trying to get space-time, 3 or 4 dimensional space-time, our world, coming from a random substratum underneath. And they say that, go look at the article if you like. By the way, I have a link to it on my website. If you go to my website, the first link on my website is to this article, Random Reality, in the New Scientist, or Get the New Scientist, right? And the reason I'm mentioning this article is because these physicists say, well, this article was inspired by work on the limits of logic. We're trying to absorb this stuff, but the physicist says, you know, Gödel really, I mean, physicists were interested in Gödel's result, but they couldn't relate to it. It's not in terms that make sense to a physicist. But it's all my fault. With my work, this makes sense to a physicist. It's not surprising. I got the idea by reading physics. And so they're taking it, so it makes sense to him because it's an idea that came from his field and is coming back to his field. And he's saying, let's go all the way. So apparently, I'm partly responsible for this crazy piece of... Now, actually, they don't use my definitions or my theorems at all, because I was asked to, to referee the paper, and I had to say this has really nothing to do with me. I mean, my stuff is mentioned in the introduction because it was, it helped to encourage these people to do this work, but really, their work is a piece of physics, and it has really nothing to do with my area. But I just thought this is an interesting example of the fact that, you see, crazy ideas sometimes have consequences. So as I said, formal systems did not succeed for mathematical reasoning, but they succeeded wonderfully for computation. So Hilbert is the most incredible success in the world, but as technology, not epistemology. So there are physicists who are interested in this notion of program-size complexity. They view it as another take on thermodynamical entropy. There's some work on by real physicists, on Maxwell's demon, it's called. I just mentioned these names for those of you whom this means something. So, but let me say that I think philosophers have not picked up the ball. Logicians, I think hate this, detest this. And I've become I'm like pornography. I'm sort of an unmentionable subject in the world of logic. So because this is so disgusting that they. So this is the story, and so what I want to say then is there's a German author who, I don't know the whole background on this, but it's something like beware of ideas. And I think it's really true. This idea of formalization, of going to the complete formalization, which was for epistemological reasons. This was a philosophical controversy about foundations of mathematics. Are there foundations? And in a way it failed, this work of Gödel's and Turing's. But here we are with these complete formalizations, which are computer programming languages. They're everywhere, right? They pay my salary. They probably pay the salary as well. This is the computer science school, the School of Computer Science, right? They pay all of it. It all pays for all of this, right? Here we are. So it worked. In another sense, it worked tremendously. And so I like to apologize in a sort of an aggressive way about this field. This field, I don't think, has applications, I like to say. I mean, the most interesting thing about program-size complexity is that it has no applications, that it proves that it cannot be applied. Because you can't calculate the size of the smallest program. But that's what's fascinating about it, because it shows limits. That's what has to do with epistemology, limits to what we can know. But more seriously, I think the moral of the story is that deep ideas, you know, they don't have a spin-off in dollars right away, but sometimes they have unexpected consequences. And I never expected to see a paper by two physicists referring to my stuff. So who knows? You know, I think it's true that the computers pay for our salary, but it's also true that there are a lot of fascinating ideas, and some of them are not very practical. But sometimes when an idea is so beautiful, I've been having wonderful conversations with people here. As, you know, someone told me today over lunch, you know, this idea is so beautiful, it's got to be right. So those are the ideas to watch out for. Those are the dangerous ones that can transform the society. This little idea of a web, for example, linking stuff in the web, you know, or this idea of formalizing, have completely artificial languages, because then it becomes mechanical to see what they mean. Very dangerous ideas. Thanks very much. Sure.
So first of all, I'm not a physicist, and I think omega is way cool. That's
Thanks, Stephen.
Computer scientist and electrician. Also, of course, Bob Solovey, one of the greatest physicists in the world, thinks that the whole theory is way cool, as you well know. Also,
Solovey is a set theorist, leading set theorist.
It's also not true that it doesn't have. I mean, the questions you're asking don't directly concern practical applications, but there's this entire book by Lee and Dasani all about applications of these theories. I mean, the situations where you actually do get, and actually in some cases, amazingly, algorithms or things out of this perspective. So actually, I mean, it's amazingly fertile stuff, even from a practical point of view. I mean, you just can't help yourself. So.
Right. Well, in addition to this hobby of mine, which is what I'm telling you about, to earn a living for many years, I was a hacker at the Watson Research Center, involved in real stuff. And I love to program computers. And so my two latest books on this subject are books on philosophy, epistemology, limits of knowledge, right? That's what epistemology means in Greek. And they come with software. You know, there aren't that many books on philosophy that come with software. In fact, this software now, since I realized that no one was running my software, what I finally did is I wrote it as a Java applet. So in my website, you have my Lisp interpreter, and you don't need to download and install any more my software, because I didn't think enough people were doing it. So I decided I'd make it available on the web. So, so the practical world and the theoretical world mix together in invigorating ways, to agree with Stephen. Yes?
I wanted to understand more crisply your result that you described very strong terms. By the way, the athlete would like the presentation without program size complexities. The way I understood where the quantifiers were, it was that there is no program for which you can assert a lower bound.
Yeah, it's more precisely, if you have n bits of axioms, you can't get any lower bounds on specific objects that are larger than n. So in other words, to be able to prove that something needs programs of size n, you need n bits of axioms.